Okay, you can resume second now.
Okay, let me just erase this thing. So I left here on purpose the formula, so then we have it for comparison later. So going back to our black holes, which I put here, you've seen that, so if one computes the black hole entropy, something that explicitly in terms of the charges, some very ugly function, complicated function, it's a nested square root, like something plus something, and then you have to check that indeed in a suitable range of parameters, by tuning the charges in a particular way, the entropy is positive. However, you can rewrite this entropy in terms of an extremization principle, which is very suggestive of what you have here in the partition function. So indeed, for a magnetic black hole, if you define, so I defined before this Z quantity here. That's why I kept it here, because it's useful for later. So this quantity here, which is dubbed the central charge, for this theory, can be rewritten at least in the case in which you have, like, at least in this specific solution, which is of course like a very small subset. It has real scalars, it has only magnetic charges, but at least for that, you can rewrite it in a very easy way. In terms of a function, I call it, I call it curly R, just so then we don't really mess up with other Ricci scalars and so on. This is just a function which is defined in this way. Sorry that for me, indices lambda, sigma, or indices I are the same. They all run lambda from 1 to 4, and also, like, let's say I, big I, from 1 to 4 as well. Sorry that notation sometimes is a bit tricky, so maybe I can just define it all with the I here. So where this Fi, if you remember, Fi are the derivative of the Fi are the derivative of the symplectic prepotential with respect to the holomorphic prepotential, with respect to the sections. In particular, Fi for this kind of model, like for the kind of model that you have here, F is equal to minus 2I, x1, x2, x4, is exactly equal to minus I, x1, x2, x3, x4, over xi. So it turns out that, so we have to, in our particular supergravity, like this is a particular supergravity model that we have into consideration, but in general, like this coordinate here, this xi, were just projective coordinate on your manifold. So in general, you can choose a normalization factor. So the physical scalar are obtained by taking ratios of xi. So what we can do is that we can choose our sections such that they are normalized xi to be equal to 1. And we also have set g equals to 1. So this is the gauging coupling constant. So if we perform this choice here, we have exactly that. The quantity r is extremized at the horizon. So if we derive it with respect to sections at the horizon, is 0. So this is the quantity which is defined everywhere. If you know it, it's defined like, okay, by taking the central charge and stripping it off with respect to some of the, like the factor proportional to the Kähler potential. So this one is defined everywhere, but it's in particular extremized at the horizon. And it turns out, quite surprisingly, that this quantity at the horizon coincides with black hole entropy. So in other words, like, again, the black hole entropy is proportional to, I'm just dropping some of the factors which are not super relevant. provided, again, that this condition holds. Sum over I, xi equals 1. So then you really see some similarities, right? So the black hole entropy is obtained by extremizing this function. So I mean, actually, from this function here, once the xi are computed at the horizon. And the partition function has that form there. This condition here needs to be imposed in order for the black hole entropy to be described as this. On the other hand, we also have this circled relation that we have there on the top. So this indeed relates the fugacities that appear in your partition function. And you see that there is an exact parallel between this condition and that. So this suggests that if we take the following choice for the section, so this was found, by the way, by Benini, Christoph, and Zaffaroni. In, I think, 15. So indeed, if we take the following parametrization then of the sections, so okay, let me just, okay, I'm gonna keep this maybe and then, x4, this is also, I mean, okay. So if you make the following, so I goes from 1 to 3, and then there is the fourth coordinate. If we make this identification, you exactly have that the value of the fugacities at the critical point over 2 pi exactly equal the value of the section at the horizon. And again, also delta 4. So where this delta bar, they are the fugacities that extremize this quantity here. So we have established, indeed, an exact correspondence between what is in the, like, the variables that appear in the background fields, which then appear in the partition function of a BGM, and the value of the scalar fields, or the value of these sections, these, let's say, projective coordinates or homogeneous coordinates, once we choose a particular parametrization of them in terms of the scalar fields.
Right. So what happens in general for general polarization? So do you break? What's the reason why we have to impose a sum over xi is equal to 1?
Because basically, it comes from here. Let's say. So if you massage this equation here, the attractor equation can be rewritten in terms of di z over L. But if L, so this is e to the k r, and this is, sorry, k halves. This is e to the k halves, exactly sum over xi. Sorry, this is like equals. I'm a bit sloppy. Do you see what I mean? So if these are equal to I can cancel this, and then the attractor equation is exactly equal to the extremization of R. It was a bit sloppy in writing, but this is all what you can always read it in Benini, Christoph, Zaffaroni. Okay, so but it's basically, it's a way to write the attractor equation in a way that it's more suggestive, like that pretty much involves a quantity which is just the vector, not the vector, the quantity which I called R in this case. So it's a rewriting of the attractor equation in this particular solution, which is characterized, by by just a specific, for instance, in this case, we don't have electric charges, and so on. So I could use this just because the solution is very simple. But there are generalizations, like with a bit of patience, you can generalize it also to the ionic charges. But in general, this is also something, yeah, it's very important to make, indeed, to make the comparison. So it's good to see that, provided that you set that, that constraint on the sections, you get an extremization you get the extremization principle of the quantity R, which exactly resembles the building block of the partition function of the dual field theory. So basically, due to this, is like we get the relation that the black hole entropy for the black hole, which in terms of the magnetic charges, is equal to the logarithm of theta ABGM on S1 times S2, computed at the critical point, let's say, computed on delta bar, on all these delta bar A. So when I say A, like A and I goes from 1 to 3. So 1, 2, 3. I, or also lambda, goes from 1 to 4. So okay, so this in general, they match. And of course, in order to show the matching, you have to, so the black hole entropy also includes factors of G Newton. So you have to use the standard holographic dictionary for ADS4 CFT3, which states that indeed you trade the cosmological constant, which is proportional to G squared, and G Newton with this value. In other words, the n, which was the un of a BJM, is related to the G Newton and the cosmological constant that you get in 4D. This is just standard holographic dictionary that you have for ADS4 CFT3. So indeed, so let me just mention a few things before starting with rotating black holes. So in general, when you extremize the partition function here and then you plug in you get some function, like you get this function here is extremized by particular value of delta bar here that corresponds to the scalar fields at the horizon. However, this extremum here most of the times is not even a maximum. It is a saddle point. So not necessarily the black hole is the configuration that maximize the entropy. That's one thing to say. Moreover, so the fact that we use the extremization principle also has the meaning in the dual field theory of singling out the correct R symmetry in the ADS2 geometry. This is just to mention, I'm not going to dwell too much on that. Thirdly, and last, so this partition function per se is a well-defined object even without the extremization on the fugacities. So it's a partition, it's a quantity, it's an observable in dual field theory, which indeed depends on all these parameters, which a priori they are unrelated. Well, we just need to satisfy this constraint here, and there is also a constraint between the p lambda sum or p lambda pi, p lambda equals 1. But apart from that, this thing do not need to attain really these values here. So what do the other values of delta correspond to? So they don't correspond to a black hole, because a black hole is really attained for these values of the sections. So Bobev and their collaborator show that indeed you can find other configurations that correspond to the points of there that are not critical points. But these configurations, you can find them in supergravity, but they're not really black holes.
Sorry, when you correspond?
They don't correspond to black holes. They are the so-called black saddles. So they are Euclidean configurations. I'm gonna show you here that cap off smoothly in the bulk, but they don't develop an ADS2, like an H2 throat. So I'm gonna just give you a picture of it, just to give you an idea. So I'm just going to draw a picture just to give you an idea. So these are like Euclidean configuration that start from ADS, like from H4, so hyperbolic four-dimensional space or Euclidean ADS, and in which we can single out a circle and, for instance, call it an higher genus Riemann surface or a sphere, and they cap off smoothly on the IR. At least this is the picture. I don't know, I can explain you more about the picture. It was just a bit like this is something that they have pictured. So for these black saddles, they cap off as R2 times, for instance, in this case it's a sigma g, and their beta is finite. While for a black hole, so if you weak rotate the black holes that we have here, or the minimal solution that we have, you have indeed something that developed an EDS2 throat. So this geometry is H2 times sigma g. And also you attach the other Riemann surface. So in a way, configurations, let's say configurations that extremize the partition function are black hole configurations. So configurations that developed an ADS2 throat. They are zero temperature configurations in which beta goes to infinity. So once you weak rotate to Euclidean space, their near horizon geometry is of the form H2 times sigma g. But for generic, so these correspond to the values delta bar, and in general, this delta bar is equal to the sections at the horizon. However, for generic value of the fugacities, you have a configuration of this kind. So you have that indeed configuration that for which the time circle caps off at a finite radius, and here close to the point you have R2 times sigma g. So if you remember, the Euclidean geometry for a Schwarzschild black hole or for a non-extremal black hole was something that contained R2, right? It was R2 written in linear coordinates. So these configurations here are somehow, quote unquote, the equivalent of non-extremal configurations, just if you put them in, if you find them in Euclidean spacetime. So these black saddles, they cannot be weak rotated to black holes, actually, because if you weak rotate a configuration of this kind, you have some pathologies in the gravity side. So these are all Euclidean. If you weak rotate into Lorentzian, you have pathologies such that, for instance, the metry becomes imaginary. But nevertheless, in Euclidean, they are well defined, and since all the localization computation, they are done indeed on S1, they are always done in Euclidean signature. So you might expect some subtleties when you turn into, like when you relate them to Lorentzian spacetime quantities. And that's also something that will become very clear for rotating black holes. It is something that will be object of the next maybe, I don't know, 40 minutes. But so the upshot of this is that for the black hole, we can match its entropy via a computation in the dual field theory, which is obtained by computing the EBGM partition function and extremize this partition function with respect to the fugacities. And the values that do not extremize the partition function correspond to other Euclidean solutions, which are a bit funny, but you can still compute then the on-shell action of this and see that exactly reproduce the partition function. So, okay, so this is for what concerns like so-called magnetically topologically twisted solutions. This is for like the matching that is that can be worked out for static solutions. For electric solutions, instead, the one that do not satisfy the topological twist, instead we have to add rotations. Rotation, in particular, just one angular momentum. That's what you have in 4D. They have analogs in 5D, which I'm also gonna describe, just at least mention a bit. But yeah, if there are no other questions, then I will start with the rotating configurations. Okay, then let me just make some space here. So for rotating configurations, we have different branches of black hole solutions, but also what we really, what is also really important is that for these branches that I'm going to show you here, the angular momentum cannot really be switched off. So the angular momentum is necessary to have a proper, like a finite area of the event horizon. And a peculiarity of this is that in 4 dimensions, ADS black holes with angular momentum can be supersymmetric. So this is already something which is very different with respect to ADS, for respect to black holes in flat spacetime. So indeed, in flat space, for instance, just to make the comparison before going to describe the solution, the BPS bound is this, is M. This. So the angular momentum does not really appear in the BPS bound. I'm just talking about 4-dimensional flat space here. The extremality bound, however, is this. If you compute the extremality bound for instance, Kerr-Newman, is this. So you see that these two things, they are not really mutually compatible, not compatible. Because like, if you have a supersymmetric configuration, for sure it needs to solve this equation, but then if you plug this into this inequality is not satisfied, right? So it means that you cannot have a supersymmetric configuration which rotates in 4-dimensional Minkowski space. But you can have that in anti-Sitter. So let me see. And for these configurations, then, they will have, like, they are still ADS4. They will have an uplift on ADS7. But similar solutions are also in ADS5. So these are electric SUSY configurations with J different than 0. So you can generalize it to many other spaces. For instance, also ADS, as far as I know, ADS7 times S4, so on and so forth. These solutions here in 5D, they are probably the most well-known. There are the Gutowski real solutions. I mean, actually, Gutowski, Kunduri, Lucetti, let's say. So this is, like, I can give you the references, like the more precise references later. But just to say that these configurations here, while to a certain extent, also the magnetic static one generalized to higher dimensions. But for this, like, the solutions with this sort of, like with angular momentum, they were discovered like only recently in ADS4, while these solutions here were known for a very long time. And also for a very long time, they also posed a puzzle, because the computation of the partition function of n equals 4 super-Yang-Mills, the so-called superconformal index, did not match for a long time the entropy that was computed on the gravity side. So it was due to all these developments, after the developments all in 4 dimensions and so on, that people actually managed to find out a loophole in what they were doing and actually get the entropy for the black hole even in 5 dimensions. Nowadays, these black holes are very, very well studied. And actually, I think that they are even more well studied than the rotating in 4 dimensions.
Was Benini Milan that computed
Yeah, it's a lot of people. So it's like Benini Milan. There is a paper by Martelli, Murti, Cassani, and Alejandro Cabo-Bizet. There's another paper by Seok Kim, and other different, I think, also, and before the original work was by Miwalla, Maldacena, Raju, and Kinney. It's a lot of people working on that. Just that the initial paper did not actually show that the superconformal index, so from the dual field theory, did not get enough states to compute, like to get the black hole entropy. So the black hole entropy should like scale as n to the n squared. But in the superconformal index, in the initial paper that I think was in 2007, was order 1. So all the states were missing. And this was because, I mean, I can spoil it now, but it's because in their computation, they did not consider complex fugacities. While we will see that this is a necessary feature of the computation in dual field theory.
Question?
Mm-hmm.
Do there exist supersymmetric black hole solutions with no angular momentum, like static?
No.
That's not.
You need that. Actually, you will see. You can see it also from the index. I think that if you set j to 0 in index, you will not get n squared. I think that there is some sort of like a proof in that regard.
So there exist obviously supersymmetric states which have no angular momentum, but there's not order n squared the number of states.
Exactly. You don't get this behavior. You can have, as I said, other configurations such like ADS 3 times S2, but then they are different. They don't have the topology of an S3 in the near horizon. And this is correspond to the partition function on S1 times S3. This is the boundary of the rotating curve. But okay, let me see. Okay, I need to maybe skip a bit of things, but so in general, I wanted to give a bit of an overview of these black holes before starting to talk about the entropy function, but just to give the salient features. So just the salient features of these black holes. So they exist also like without any scalars. So these were already found before. So the initial solutions without scalars were by the universal solutions were found by Costelleci and Perry in '92, but then it took a lot of years to find the full class of solutions. We find them in 2009. But so basically, their New Horizon so first of all, the New Horizon geometry give you in a nutshell some of the features. Geometry is ADS2 fibered on S2. So New Horizon geometry also fits into the general form of the near horizon extremal care, which is this. So this is e to the u is a function of theta. So indeed, it depends on many more factors, but the general form is there, which means that so also the gauge field has a particular kind of form. But all of this is to say that so we are still looking at black holes which are anti-de Sitter and with lots of properties that make them different than black holes which exist in our space, of course. But on the other hand, close to the near horizon, close to the horizon, so in the near horizon geometry, they really approximate that they fall into the same category of the neck, which is which describes the black holes which are in our universe. So while asymptotically they have a negative cosmological constant, they live in anti-de Sitter space. Close to the geometry, they look pretty like something that we can find in our universe. That's why this microstate computation, they are somehow very I would say, very interesting. So in general, so I'm not going to go into detail because I think I'm running a bit of time. I'm not going to go into details on how to find the ADS4 times 7 black hole solutions with all the scalars and so on. So we have found them. In general, they are kind of complicated because to find a black hole solution like with the angular momentum, you have to also turn on, like, if you want to add matter, this matter also depends on you have less symmetry, so the matter also depends on the angular coordinate. So instead of solving, so this solution here was found by solving, this is static and spherically symmetric. This solution here is found by solving the Killing spinor, and you get first order ODEs, so equations in only one variable. To solve the equations that get this solution here, you have to solve PDEs. So it's first order PDEs, but general mathematics cannot handle, you have to do it by hand, and it can be quite involved. Nevertheless, there exist solutions which describe rotating black holes, and they are fully analytic. The entropy that you get for this black hole is something, again, kind of horrible. It is a nested square root. However, it can be, like, one of the good things that really led to many of these developments in microstate counting is that the entropy can be written as an extremization principle as well. And indeed, you can find the entropy starting from an entropy function. So this is the so-called entropy function formalism. So this is a function that reads this way. So for the most general, I'm telling you the most general solutions, that will be the equivalent of those, though with electric charge and with angular momentum. They will be, like, their entropy will be found by extremizing this function with respect to the fugacities, delta and omega. As you see, the story is kind of similar to the story that we had in 4 dimensions. However, also here, there is a constraint between the fugaces. So this entropy function depends on, of course, these are delta i's, omega. Omega sits here, is the variable which is conjugate to the angular momentum. And then also depends on the electric charge of your solution. And this is, again, the prepotential that specifies your supergravity theory. So this is, again, this thing that we found before with the square root of gamma 1, delta 1, delta 2, delta 3, delta 4. This needs to be supplemented again by the condition and this is not a typo. This is not a typo. There is an imaginary part here. So as you see that you really need this I in order to have the extremization of the entropy function to give you the entropy. So this is something a bit tricky, well, actually tricky, that will take me the next, probably until the end of the lecture. So if you take this function here, you extremize it with respect to delta and omega, this function here is extremized for complex values of delta. This is something that I will prepare also an exercise if you want to. So it's really easy to see that this function here, if you extremize it, the value of delta for which you obtain an extremum, they are complex. Moreover, if you substitute these values here inside here, you get two equations. One that gives you the entropy, rightly so. This is the black hole entropy. It turns out fine. But you also get another constraint on the charges that indeed is such that your solution is extremal. So by setting this equation here, extremizing these under this constraint gives you two equations, one for the imaginary part and one for the real part. The real part of the entropy gives you exactly the value for the black hole. The imaginary part is something. If you put this something to 0, exactly you land on the extremal BPS black hole configuration. So I'm not going to give you here exactly the full thing. I'm going to give it as an exercise to prove, given a solution, that if you extremize this, you exactly get the entropy. However, one thing is really puzzling at this point, and the fact that you have these complex values of delta I. So this delta I, in this particular case for the black hole, were thought to be indeed related to the conjugate values of the conjugate potential to the charges and of the angular momentum. So if you compute these quantities on a black hole in Lorentzian space, these quantities are real. So the thermodynamics potential for a black hole, like a very well-defined black hole, BPS or non-BPS or extremal, non-extremal, if you have a good thermodynamic description, if you compute the on-shell action and the potentials, and this like in general, the electric potentials, you compute them by taking the gauge field at infinity minus the gauge field at the horizon. They satisfy various different relations. In particular, they satisfy the first law of thermodynamics. But they are real. So on the Lorentzian configurations, these potentials, they cannot be complex. So what are these complex values of delta I? Are they related to the thermodynamics? Notice also that you really need complex values of delta I for the entropy function to be extremized on the value of black hole entropy. And you also need exactly complex values of delta I in order for your indices, for the partition function in the dual field theory, to have the correct behavior and to match the entropy. So if you don't impose if you don't do the computation with delta I and omega I complex, you have that the superconformal index, so the partition function of a BJM on S1 times S2, it's similar to the other twisted index that I gave you before. The algebra is it's a bit different because the supersymmetries arise in a different way. But if you compute them with delta real and omega real, this does not scale as n to the 3/2, but it scales order 1. So you really need to have this thing complex, but then how to make sense of these complex quantities in the gravity side. So this will remain a puzzle for a number of at least months. So in the original paper that computed the superconformal index, indeed, they were taking into account these objects to be real, so they could not really match the black hole entropy. But so some people, I'm gonna give you the reference now, came up with a very clever way to map black hole entropy and to figure out what's the meaning of these particular thermodynamic potentials, which are this delta, in function of black hole quantities, to map this delta directly to their value in the bulk. So as a disclaimer, they will not be exactly the thermodynamic potentials, so they will not be exactly the chemical potentials and the angular velocity computed in the bulk, but there will be some complexification of those in a particular way. So let me see now. How much time do I have? I have the last 2 pages, but...
yeah, I think you can have 15 minutes.
15, okay. Yeah, I need to write down quite a bit of formulas, but okay, so I'm just going to write down to see which kind of solution we work with. So I'm going to give you the full solution. Once again, it's going to be the last full solution that I give you, because tomorrow I'm going to just talk about probe analysis, so it will not be a solution like this. So bear with me for the last time. Yeah, the solution with rotation, they are quite involved. So it's like a generalization of the Kerr-Newman solution, which, as you can imagine, has a lot of work factors and lots of bells and whistles. these solutions were treated in so Cassani, Paplini. So they were already known, the solution themselves, but how to match their fugacities to the field theory computation was not known before. So this is, I think, is 20. No, I think it's in 19 probably. And the original paper was by Cassani, Cabo, is it? Also Cassani, but Murti, Martelli, et al. And that was in 18. So this is 5D. And this is in other D, like D, in particular D equals 4. So the solution is parameterized then by the following numbers. So you see that solution is parameterized by M, M, A, and 2 delta, so delta 1 and delta 2. This is an ADS4 rotating black hole with 2 electric charges. Obtained from the prepotential F equals the root of x1, x2, x3, x4 by making the fields coincide 2 by 2. So this is called the pairwise equal charges. It's a solution which has angular momentum. It can be BPS. You have to impose specific condition on the charges for your solution to be BPS, but you can compute all the thermodynamic potential. So this in general, once you write the work factor in this way, it corresponds to a black hole with no zero temperature, normal, like it corresponds to normal black hole with mass. You can tune the mass, you can tune the angular momentum and the charges. But so the black chemical potentials, you can compute them and they are real. And also the angular velocity, which I call omega, is also real. As I was mentioning, this solution satisfies, of course, the first law of thermodynamics. Once you compute the charges, the mass, and also the other things, and these thermodynamic potentials, so there is no reason to believe that this solution is pathological. It's a Lorentzian solution. It's well defined. So if you impose supersymmetry, so condition for BPS is this one. And if you impose this condition plus this, you get an extremal BPS solution. So BPS is this one, is the condition for extremality, equal extremal BPS. Then you compute the chemical potentials for this. Phi star 1 equals phi star 3 equals omega equals 1. This is not some sort of like symbol that I use. I mean, so the chemical potentials for the black hole solutions on the BPS solution are just 1. There's nothing complex about them. So how come, so do we relate these chemical potentials to the one that are coming from the entropy function? No, because they're clearly different. These are just real quantities, satisfies all laws of thermodynamics and so on and so forth. So it means that we have to engineer some other way to relate. Probably the chemical, like what we think at this point is that the chemical potentials that appear in the extremization of the entropy function, they're not quite the one of a black hole in Lorentzian signature. So we have to resort to some sort of complexification. And these people, like the people, Cassani, Papini, and so on, engineer a clever way to follow a supersymmetric trajectory without imposing extremality, normalizing in a particular way the fugacities. One actually turns out that it's going to be able to match the fugacities that you get in the entropy function to the one of the particularly, like appropriately complexified solution with some sort of like a renormalization scheme from the fugacities. And this is one of the last things that I'm gonna show you here. So what Cassani and Papini did is that they imposed the BPS condition, but they did not impose the extremality condition. So let's erase this. So I denote it, by the way, with a star. So once I call stuff with star, or the asterisk, it means extremal plus BPS. So this will be useful later. So he doesn't impose, so impose only this, does not impose the extremality condition. So what he does at this point is that from the condition delta R, so he founds a condition on M, starting from delta R equals 0 in function of the radius of the event horizon. So if you don't impose the extremality condition, this particular kind of like a relation, the one that you get from delta, if you don't impose the extremality condition, in general, BPS can be either a naked singularity or something which is not really well defined. So without imposing extremality, the value of the mass and R plus, in principle, could even be complex. That's what we mean by allowing complex parameters in your solution. Because you have in mind to analytically continue, or to, in any case, like you're doing a computation in the Euclidean, where the metric itself, which contains all the parameters, could in principle also be complex. So without imposing the extremality condition that was here, we find the mass from delta R. There's this value here, which shows that it's indeed complex. So the mass is complex. For this, so given these values for the mass, if we plug into the relation, if you plug into the chemical potentials, which you see that they contain the mass, they become complex, and therefore they start satisfying this relation here. At this moment, all the quantities here that we deal with are complex. And you see that starts getting more similar with respect to the constraints that we had before in the entropy function. So we introduce now different variables. So we define omega as beta, which in our case, once your solution is extremal, beta goes to infinity. So in order to cancel the divergences that arise when we multiply by beta, we have to subtract omega to omega its extremal BPS value. Then we want to actually tune our value to the BPS extremal, but for the moment we keep it this way, in such a way that the divergences from beta is cancelled when we go close to the extremal VPS value. And the same we do it with phi I. We define them as, again, beta phi 1 minus phi I star. In this way, we get exactly the condition that we had before. I think that before I wrote, okay, let me see. Phi 1 plus phi 3. This is like also 2, phi 1, phi 3, equal minus and plus phi I. Moreover, we have that if you compute the on-shell action, we can find them written in this way. So we write the on-shell action. This is exactly the same procedure that we had before. We plug the solution, I mean, with a bit of care, of course. You have to plug the solution into the action, renormalize, and do all sorts of things. But you see that once you get this, you can rewrite everything in terms of these variables here. And now, after you have seen that you can rewrite things in a similar way with respect to the VPS, to the constraint here, you send R to R VPS. R star, for instance. And it turns out that I, the on-shell action, turns out to be 1 over 2 phi 1 star, phi 3 star, over omega star. This is again equal to also from here minus S star minus omega star J star minus 2 phi star, right? So and if you see from here, it's something, it is exactly what we wanted, right? Because it looks then that the entropy, so this S star for the VPS solution, let me just erase here. Yeah, I will write down the solution. You will find it also in the exercises because we're gonna. I'm just gonna give you one thing to extremize the entropy function. I think it's easy to do and easy to see that it coincides with the black hole entropy. But basically, the upshot of all this is that we can find a consistent definition for the variables that appear in the entropy function by taking suitable complexification of our black hole geometry and by subtracting the BPS value, by defining these variables here, in which the divergence due to beta goes to infinity when you reach the extremal VPS solution is actually compensated by subtraction of the extremal VPS value. And therefore, and also you see here that these exactly coincide to the prepotential that we had before, delta 1, delta 2, delta 3, delta 4, once you set these two equal, and also these two equal. So I erased the form of the entropy function, but you see that the entropy function is indeed equal to then I on shell plus J plus phi Q phi 3 Q3. So in general, but in this case, we have seen indeed that this entropy comes indeed from the on-shell action, which we have computed as here, and indeed the form of this on-shell action is something that goes as the root of delta 1 to delta 3 delta 4, and needs to be divided by omega. And if you check back what I've written before, is exactly the form of the entropy function that we started with. So by defining our fugacities in this way, we see that indeed the entropy function is a so-called Legendre transform of the on-shell action, which is written indeed in this form. Once you know So if it's not really clear, is that this is just equal to delta 1, delta 3. So you can relate this thing exactly to variables here. Sorry, this is just omega. Okay. So this is a bit clear, but so the upshot is that in these variables, we managed to see that indeed we can find the entropy by extremizing a function which is nothing else than the Aushel action written in these particular variables. These particular variables coincide indeed. This particular definition of the potential exactly is made in such a way that the values for deltas for which the entropy function is extremized coincide with the value of the chemical potentials which are defined in this particularly renormalized way. And even for the BPS solution, these potentials here will have an non-vanishing imaginary part. So indeed, they exactly match the complex values for the chemical potentials that appear in the extremization of the entropy function. So with a bit of craft, let's say, with a bit of, manipulation on the complex solution, we have seen that there exists a way to define this chemical potential in such a way that you have complex values, and these complex values are exactly the one that the extremization principle tells you that are related to the black hole entropy. In a bit of a convoluted way, but this I think it's a subtlety that arises due to the fact that all the computation in localization are made in Euclidean signature, and to relate them, and there are some subtleties in weak rotating, especially like in particular this configuration which have angular momentum. So you have to be a bit careful that the mapping between parameters, Euclidean and Lorentzian, is not that straightforward. But apart from that, it seems that yes, so people have computed the superconformal index, and indeed it has really like this form here with n to the 3/2. So indeed, by extremizing, by Legendre transforming the superconformal index in the dual field theory, one exactly gets the entropy of these black holes. And also for ADS5 black holes, this is for ADS4. And for the ADS5, again, by computing the superconformal index with complex fugacities, one also has, this sort of fall-off here. This is for ADS5. So this is a superconformal index for n equals 4 superior mills, which is dual to black holes, which are rotating with 2 angular momenta in ADS5 times S5. So the matching was performed both in ADS4 with a bit of caution, because the computation here is not very much on firm grounds, because they make some funny limits, like they send omega, they use the Cardi limit in which omega goes to 0. So it's a bit tricky, but in this situation, the computation of the superior Mills superconformal index is on very firm ground. There have been many people studying it, but as I was mentioning, Benini Milan, Cabo Bizet and Martelli, and many other people, like Seo Kim, the entire group of Korean people, like at Kias, and so it seems that this result here is on very firm ground. So upon taking into account complex fugacities, you really manage to get a hold, or to manage to get the match between the superconformal index and the black hole entropy. We are still a bit far from here, but like the original the only computation it's available is by the group of Seo Kim at Kias, that indeed seems that he managed to get this formula, provided that he takes omega to be very small. But there are some, talking to the expert, it seems that you need to put some things a bit in a firm ground in order to perform this limit, but in any case, at least the number of states and to the 3/2 seem to be there. Therefore, it seems that also for ADS4 black holes, you have the correct number of states that reproduce the black hole entropy. So yes, I think probably.
Okay, quick questions.
So typically, because these data are complex, if you extremize, the extremum will also be some complex. So the entropy will be some complex number in general?
In general, yes. The point is that you have to, the entropy will have an imaginary part and a real part. So if you set to 0, the imaginary part is exactly the constraint that that avoids, like people say that it avoids closed time-like curves. So it seems that by setting to 0 the imaginary part of the entropy, after you get it from the entropy function, it tells you something physical. It gives you a further constraints for your solution to be physical. And so if you set it to 0, you have only the real part, and this matches with black hole entropy.
Right, but yeah, this part will always confuse me. So in this formula, it looks like you have 5 different parameters, right? But in reality, because they are constrained with this 2 pi, right, there's only 4 different parameters.
Exactly, there is a constraint like that one, but yeah.
Right, so when you extremize, you will get in general an S which depends on 4 parameters. Now I'm setting the imaginary part of S to 0, so that should in principle reduce it down to 3 parameters.
Yes.
So, but the black holes are parameterized by 4 numbers, the general supersymmetric black holes.
Okay.
How is this? So I've always been confused about this counting. Like there are 4 parameters in this here. When you extremize, you'll get 4. But now I'm setting the imaginary part of S to 0, which imposes an additional constraint. So now I should be getting an entropy that only depends on 3 parameters.
Okay.
But the black holes have 4 parameters in general.
Exactly.
So how is the counting working then?
Because then you have to impose this further relation between parameters to get rid of this closed time.
But that's coming from the imaginary part of S equal to 0. So after imposing that, you have 4 parameters on the gravity side.
Okay.
So that's why I'm confused about how this counting is working out. So because for 5D supergravity black holes, because there's Q1, Q2, Q3, J1, J2. So there's 5 parameters to begin with. And then you have this closed time-like curve condition, so that reduces it down to 4. So on the gravity side, there should be a solution. The most general, smooth, supersymmetric solution is dependent on 4 parameters.
Okay.
But from the index side, it looks like it should be 3, because you have 4 potentials, 4 independent potentials, which you then do Legendre transform. You get some S, which depends on 4 numbers, and then you additionally impose the imaginary part of S being 0, so that should reduce it. So this
exactly.
But I think confusion for me.
So I'm not sure that this condition that you get from the imaginary part being equal to 0 coincides with the extremality condition, right?
It coincides with that no closed time-like curve
exactly.
condition.
Yes.
That exactly.
Yeah, exactly. But is this equivalent to the extremality condition or not? Because in 4D, I think that it's equal to have an extremal configuration. But if you want, I'm gonna do this as an exercise, like when I prepare the exercise. We can do also the 5D, so then we figure it out if you want. But I'm afraid that there is a further condition, like this closed time-like curve condition is something on top of what you call the extremality condition. But we can verify it. I think it should be easy to see given the entropy function, and we can maybe do it tomorrow also.
Okay, let's thank Chiara again. We reconvene at 2. Yes.